speaker in our workshop will be Laura De Carli from Florida International University, and she will speak about stability of exponential systems and Fourier matrices. Please.
Yeah, so first of all, I wish to thank the organizers for inviting me to this incredible workshop, and like my predecessor, I also wish to thank all of you for still being here. This is the last talk, and yeah, the workshop was very long, so but very productive for sure. So today I would like to talk about stability of exponential systems and Fourier matrices. This is a joint project with my PhD student, Oleg Azikchuk, and with Weilin Li from CUNY. He's an applied mathematician who actually gave a really gave shape to this project. But let me start with introducing the protagonists, that is the Fourier matrices, first of all. More importantly, many, of course, everybody probably know what Fourier matrices is, but I would like to write that on the board for the notations, because not everybody uses the same notation for Fourier matrices. So a Fourier matrix is a matrix in the form of F, omega u, whose elements are exponential function of argument e to the 2 pi I omega dot u, where omega belongs to omega and u belongs to capital U, and the size of omega is equal to, say, n, and the size of u is equal to L, for example. So this is a matrix which is a n by L matrix, right? Not necessarily square. So the set, well, actually, U is rather in T, which is the, so T is the set of the complex number such that, of unit measure, right? So it's a kind of the unit sphere. And the omega is in ZD, is made of integers. So the set, the elements U are referred to as nodes, or U is the node set, and U is the frequency set. So a notable case of Fourier matrices is when the elements of omega are the integer points in a square of size m. Well, actually, or in general, a rectangle of size with sizes m1, m2, md. And the omega are like points on the unit sphere, typically. So this matrix is special, and it is also called the unnormalized discrete Fourier transform. Its columns and rows are orthogonal. It has a lot of nice properties, but I will not go into this topic here. So special cases of Fourier matrices are the so-called van der Monde matrices. So which are, in a way, they are, unidimensional. While the general Fourier matrices depend on parameters in multidimensional space, the van der Monde matrices, which, I'm going to write it here, are depend on a parameter, on parameters xk, which are in R, say, or in the unit circle, in the unit circle T, and the number j is just an integer in arithmetic progression. So these are the matrices whose elements are e to the 2 pi I j xk, right, where j goes from 1 to L, say, and L is the number written here, and k goes from 1 ... to n, right? Again, van der Monde matrix can be rectangular or square, depending on the number of elements xk. So these are, of course, special Fourier matrices, and the van der Monde, it is well known that van der Monde matrix has rank n, if and only if all the x-case there are x-case elements which are distinct. In fact, there are...
N should be bigger than n.
Sorry, I didn't say that. Yeah, it has rank. It has maximum rank. Actually, I should have said right. Yeah, sorry. And actually, n is not necessarily bigger than L, but yeah, it is. So I should have written here maximum rank. Say, yeah, typically it's. So these matrices appear in many applications, actually many more than I was aware of when I started, working on this problem. And their properties are, really appear in problems in super resolution, for examples, and interpolation, etc., etc. But now let's introduce the other protagonist of this talk. That is an exponential system. What is an exponential system? So an exponential system is a set of functions in the form of e to the 2 pi I times n plus delta j, where delta j is it's not necessarily an integer here, right? It is a vector in which we can take z delta j in again in the unit sphere in RZD of mod ZD, and then it is in Zn. So let me write this definition down because we might need it later. So j go from 1 to L of e to the 2 pi I n plus delta j x, where n is in ZD, right? So, of course, when we are in dimension 1, and jd and delta j, again, is in R mod z to the power d, right? So, of course, when we are in dimension 1, and when delta j is equal to 0, so in other words, when we have only one delta j, then we have the standard orthogonal system, right? Which, as we know, it is a Fourier basis on the unit interval of 0, 1. So in general, this set can be, it's a set of exponential, but its properties are determined by the domain on which we define that, on which we consider the set. So the domain we are considering is a union of cubes which are, say, we consider n of them. As you see, like, there are the parameters n and l that are recurring in this conversation, right? Which are, like unit cube with center at P1, P2, P3, etc., right? So, and this is the, for example, Q plus P1, right? And this is the Q is the unit cube, so 0, 1 to the power d, right? And pk, the pk is very important, are in ZD, so they are integers. So now I wrote down, because I know that notation can get confusing very quickly, so I've decided to write all of the notation that I'm using on the board, so I will keep referring to them. So, like I said, the characterization of what this exponential system is, of course, depends on the set where it is defined. So let me recall very quickly, because everybody knows, I guess, what these definitions are. So a set of vectors is its sequence if basically the vectors are, roughly speaking, linearly independent. So for every linear combination of these vectors, then there is a lower bound, like a times the sum of the square of the coefficient, and which implies that the linear combination of vectors can be 0 if and only if the coefficients aj are all 0. So that is kind of an enhanced version of linear independence, right? On the other hand, a set of vectors is a frame if the sum of the inner products so for every element w, so the sum of the square of the inner products with the elements of the frame satisfy the frame inequality 4, which again, so the lower bound implies the completeness of the system in the Hilbert space, because if all the inner products are 0, if and only if the vector is 0, right? That is what it implies. And the system is a Ritz basis if it is both a Ritz sequence and a frame. But as you can see, I mean, a Ritz sequence can have fewer vectors than a basis because, again, linear independence, right? We want the linear independence. And the frame can have more vectors than a basis because, you know, we don't care about, care about the completeness. Now, let's connect the two protagonists, right? So we associate to the exponential set B delta that I defined here. So B delta is kind of characterized by delta J's, right? And the pKs, right? So the delta J's and the pKs, which are kind of quote-unquote the translation vectors of the cube. So we produce a Fourier matrix associated to this set, right? And the Fourier matrix is, so let me write it on another board. So the Fourier matrix is, we call it gamma, or, sometimes for an excess of, letters, we call it like the gamma delta p, so 2 to the pi I delta j pk, right? And then we show that, it was well known, but that was already in the literature, right? That the properties of the matrix translate into the properties of the exponential system and vice versa, right? So, one last thing before I change slides. The singular values of the matrix gamma are denoted with sigma 1, sigma 2. This is a standard notation, right, for the singular values. So, and here is the theorem, right? So the theorem says, this is a more general than the one that you can find in the literature following the references. In fact, some of the parts we proved in our paper, but because we weren't sure if we were known or, or where we were available or not. So we consider the matrix gamma, right? And we show that if L is greater than N, i.e. if there are more delta J's than pKs, then the set is a frame on the unit of the squares Tp, right? Because there are more exponentials than we need in a way. And on the other hand, if L is less than N, i.e. if there are fewer delta J's than pKs, then the set is a Ritz sequence if and only if the associated matrix has rank L, i.e. it has maximum rank. And the optimal frame constants of the system are the maximum and minimum, the square of the maximum and minimum singular value of the matrix. So again, this theorem is well known, at least for square matrices it is well known. It is available, and you can see it in various places. So here I'm citing one of my papers, but there are also references where this theorem appears, etc. So, in particular, this theorem implies that in the square matrix case, that is when n is equal to L, the system is a Ritz basis if and only if it's a frame, if and only if it's a Ritz sequence, and if and only if the matrix is non-singular, right? So the square basis was known, but there were also results by Shahavnitsa, Nolesky, Ulianowski for rectangular matrices that were not quite related to what we're going to do now with these systems. So this connection between exponential systems and matrices is very powerful, and there is, I feel that there is a lot of work to do. In fact, the work that we did is kind of a small fraction of what we could have done and what we discussed at the very beginning of this project But for this project, for the paper that I'm presenting, we focused on two specific questions. So how do the estimates of the condition number of van der Monde matrices translate into statements for exponential systems associated to these matrices? So in other words, how to go from matrices, in particular from van der Monde matrices, to exponential systems. And the second question is how to view there are results on the stability of exponential systems that are known, and I will recall them in a moment. So how do these stability results apply to the stability of the corresponding matrices? So the reason why I'm focusing on van der Monde matrices is that there is a lot of literature on them, on these matrices. But there is very little on the Fourier matrices. So, we try to do some work with general Fourier, but, we ended up going back to the van der Monde matrices because, again, they are better studied and their properties are easier to understand. But, again, there is a lot of more work to be done. So the theorem 2 that I cited here shows very clearly that the good condition, it's easy to see, like take a square van der Monde matrix, right? When the matrix is singular or not, right? Because the xk's, like I wrote over there, right? The xk need to be all different. But it is not easy at all to see whether the matrix is well conditioned, i.e. whether the ratio between the maximum minimum eigenvalue is somewhat stable with the dimension of the matrix, right? And so the theorem shows that the condition number of the matrix depends strongly on the separation between the nodes, i.e. how far apart are the xk's in the definition of the van der Monde matrix on the unit circle, right? And so, we have a good bounce, right? The maximum minimum eigenvalue are close to one another if the separation is pretty large. So unfortunately, we get something non-trivial, right? If if only L is greater than n, i.e. if we have the matrix is kind of wide and shallow, right? So it's for square matrix, square van der Monde matrices are notoriously badly conditioned. So, however, here is a result by Weilin Lee. Oh no, I'm sorry. Yeah, this is so. We can use this theorem to produce like an estimate of the Ritz bounds for Ritz sequences. Like I said, the previous theorem works for matrices which are kind of wide and shallow, right? So the translation. So if we view this matrix as a gamma matrix for the exponential system, it will give us a matrix with a lot of pk's and few delta j's. And so that gives us a theorem for Ritz sequences, which is exactly, what one expects, right? The maximum minimum singular value of the Ritz sequence are the singular value squared of the singular value of the matrix, and we have the estimates from the previous theorem that can, can be applied. When the separation between the between the nodes of the matrix is not as nice as in the previous case. So then there is a result by my co-author Weilin Lee, who shows that, there are other results in the same direction, but yeah, his result is probably the last of the series and the more complete, in my opinion. So that it is enough to consider the so-called chunks of nodes of the xk's, the nodes xk. So if there are if the nodes are kind of grouped together in a in a smart way. Like say, suppose for example that that applies of course to very large matrices, right? So if the nodes are like this, right, there is a chunk here, and then there is and the nodes are very tied together, right? But they can be divided into groups that can be like they have a good separation. Right, then we can still prove, we can still show that the matrix is well conditioned and get a good estimates on the singular values. Unfortunately, once again, the matrix, L tells you how many columns we have, right? The matrix is large and squat. In fact, L must be greater or equal to 6n. For this, and then that translates into a result for Ritz sequences, which again what we did in our theorem, in our corollary rather, is to kind of connect, find an exponential system whose gamma matrix, whose matrix is associated matrix is exactly a matrix with the properties of the one in the previous theorem. Questions so far? 8 minutes, oh mamma mia. So because I want to go to the next question here, and that is the stability. So how do known results on the stability of exponential systems translate into results for the Fourier matrices and vice versa? So we're hoping actually to do the vice versa, that is to jump start on the results for stability for matrices, but it turned out that it was, according to Veilin, who, like I said, is the one who really gave us a big impetus, like a big, like the direction of this, for this problem. It is far more significant to use the exponential systems to produce stability results for matrices, because there is very little in the literature, and there is interest in the people who do super resolution and apply van der Monte matrices extensively for the applications. So, but before I start with that, let me recall the so-called, the basic Kadek theorem. So that was proved by Kadek to show, to prove it's kind of an optimal result, optimal stability result for the trigonometric system on the interval 0, 1. So the basic trigonometric system is like, e to the 2 pi I n over x, right? So the interval size n, right? And then we added this disturbance, the disturbance delta n, not to be confused with the delta j here, okay? The delta j and the definition of B are do not depend on n. They are depending on, they're completely independent, right, from n. But in this case, the disturbance depends on n, right? I mean, for every n, there is its disturbance, delta j. So the system B in the theorem 6 is an exponential basis if the supremum of the disturbances is which less than a quarter, and a quarter cannot be improved, and that is a famous example by Levinson. So that doesn't mean that there are not system, like for special delta j's, right? The result can be improved. But this is the more general case, and of course that has the narrower stability bound, right? But there are, like I say, I'll say in the next slide, so it's possible to improve Kadek theorem at the cost of making some assumption on the delta j's. But let me show, how we can use Kadeks to prove stability result for the matrix. So this is actually, so to this matrix here, right, we can correspond, so we can make correspond a van der Monte matrix, which notes e to the 2 pi I k plus epsilon k over n, because, we can think of, the Kadek I stated, right, it is on an interval 0, n. So we can divide the interval 0, n into, unit segment, and so that will be P1, P2, P3, blah, 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 right, Pk, right? which form, of course, an arithmetic progression. So if we consider the matrix gamma associated to this exponential system, of course, it's a Van der Monde matrix, right? So by Kadek's theorem, we know that this is the matrix of an exponential basis, provided that the epsilon k, which now we renamed epsilon k, right, will be less than a quarter. And so we know that the perturbed, Van der Monde matrix is invertible, and its extreme singular value actually satisfy are exactly the frame constant of the basis. So we go from bases to matrices using the result that actually were known since the 70s, actually. And by comparison, so that is, what made my co-author, Veilin, really excited, because that was the best available before our result. So the stability, so these are like the singular values of the matrix, not unperturbed matrix and the perturbed matrix. And the constant C omega p, which is the sum basically of all the omega j's squared, right, can become very large very quickly, right, if there are a lot of omega j's. Plus there is also the square root of n. So in other words, we need to, in order to get a meaningful result in this theorem, we need a very, very, very small epsilon. And the larger is n, the smaller is epsilon. So, which is not the case for the theorem that I just presented. But time is passing fast, so let me tell you about some generalizations. That is what I said before, right? If we make some assumption on the delta j's, so like the perturbation, so for example, if the delta j is kind of a periodic, instead of depending on n, depends on, is in the form of j times delta, where j is an integer, and there are n of those integers, then we can have a better Kadek in a way. So in other words, we know that this is a basis. So for that to be a basis, it's enough for the inner product, the difference of the pKs times this parameter delta that, that measure the disturbance, not to be an integer, right? And unfortunately with this theorem doesn't allow to estimate the frame constant as nicely as the other one, but we know that that is going to be like a basis, but the frame constant are a bit of a mystery. I'd rather actually, I'm thinking I have a minute and 18. So I wanted to present so here is a multidimensional version of the Kadek theorem, which actually it is not ours. It is proved by Sun and Zhu. So the part A is due to Sun and Zhu, and the part B is actually due to Balan. And but unfortunately, the limitation of Kadek's theorem, the current limitation, is that it is known only for bases on the square, on square domains. There is nothing like Kadek theorem for any other domain where exponential bases or even exponential frames are known to exist. So all these results, in fact, see the domain is 0 n to the power d. So we have a slightly more complicated version, but it's for a rectangle, we can generalize Kadek. But if we don't have a rectangle, we don't know what to do. So more work, I feel that a lot of research should be done in this direction. So like I said, I was acknowledging the authors of the two parts of the theorem that I just stated. And then we use that to prove a corresponding result for Fourier matrices using this Kadek version. Sorry, I know that I'm speeding up, minus 0.25. That is kind of disquieting. I don't know if you think if this countdown. But I don't want to finish without acknowledging that, you know, the whole investigation was started actually by a paper by you and Tom said that again, you know, my co-author Veilin found out, and that is, you know, to applied mathematics. And then he realized that we were basically following the step of Kadek's theorem to prove a stability result for their matrices, which is not as good as ours. So we say, okay, now we have some work to do here. And we also, like a fraction of our result, like theorem 7 that I mentioned before, was proved, yeah, we learned recently, in fact in March, at a conference in March, that Shahaf-Nitzan and one of her students were working on a related problem. So anyways, this is some reference which you will see, like if you download my slides, probably. And I thank you for your attention.
Thank you for the talk. Are there comments, questions, remarks, please?
All right, I have a very naive question. If you go back to just the very beginning, just the basic setup of the problem, you have this, you know, this old, well-known result that
Tell me when to
you
stop.
have a basis if and only if no, much earlier, that you have a Reese basis if and only if the rank is bigger than or equal to n.
Yeah, there you are. Yeah. This one?
So the naive question I have about this, and this must have been done, is that if you make your shifts random, either with respect to uniform distribution or normal distribution, it must be true that generically the rank is n, and that the concentration is very, very high around the mean.
What do you mean with the random?
So your shifts of the j. Suppose you
The pKs, you mean?
Huh?
The pKs or the delta j? Yeah, the matrix is here, so.
Yes. So you have these shifts, right? So what if you make the shifts random?
No, I mean, yeah, exactly. No, you're right. Yeah, if you make the shift random, yeah, the probability that this is, say, rank n, or in the square case, it's non-singular, is very high. Yeah, in fact, I discussed that in my paper too. Yeah, the set of, say, if you consider the pKs, right? Or I mean, if the pKs are fixed, and if you consider the delta j's for which the matrix is non-singular, they form a set of measured zero, right? So, but the problem is for us is not to find the you know, conditions for which the matrix is non-singular. We do want to know about the frame constants, i.e. we want to know whether the matrix is well conditioned. And that is difficult. That's the difficult. I mean, because I mean, this is the key point here, right? The optimal frame constants are the singular value. We need good singular values if you want to have good frame constants.
So just as a quick follow-up, so you didn't. Did you attempt to compute the expected value of the frame constants?
Oh boy, didn't we try? This is in fact, Oleg and I, my student Oleg and I have been trying to do that for a couple of years. Because, you know, we have some, I mean, for the problem we are studying, we need the eigenvalues of certain matrices and the singular values of certain matrices. I mean, we need to find the delta j's that make this matrix with some, you know, certain pKs that, you know, that we have, you know, for our problem, as well conditioned as possible. And so 2 years later, I'm still here talking about it, you know. It's, yeah, this is, you know, estimating the singular value and especially finding well-conditioned matrices of this kind. It seems to be a very difficult problem.
Further comments?
So it's also about this result. Do you know if you replace your domain, instead of union of cubes, you take unions of a set?
That higher. Oh yeah. That is, that is something that we've been talking about, and we have a result that we didn't put in this paper, but because it was not connected, right? But yes, we have a similar result. We have a result like instead of considering union of cubes, what's happening if we consider union of hexagons? Yes, and we do have the same result. Yeah.
Or any other set, maybe you only need that can have a spectrum which is a lattice.
Correct. Yeah. No, we do have a more general result. No, I said hexagons because that's when we computed exactly the spectrum, you know. So, but yes, indeed, you know, the result is valid for any spectral set, any tiling, you know, spectral set that tiles with a set of translations, right? So, because we need the dual lattice. I mean, the pKs, right, for us here in these, like in the theorem I stated, belong to ZD, right? So if we consider a matrix in this form with the n belonging to the lattice of the translations, then the pK need to belong to the dual lattice. So the statement becomes a bit more abstract. For the hexagon, like I said, we have an explicit, So, but again, this is not part of this paper. Yeah, that is part of a separate project.
I think we finished this discussion now and have to thank all speakers of this morning again.